that's just great to hear. The weather here just blows.
Well, like I come down the freeway and I've got snow covering my truck and everyone's like looking at me.
Yeah, I passed. It'd be hard to see him. Oh. All right, you can probably guess what chapter 16 is about. Yep. No. Way to remember that word. Where did that just come from? Wow. All right. It's about acids and bases. It's 50-50, like easy and very difficult. Oh, great. This is the end of this chapter and the start of the next chapter are the 10. It's okay. No, you shouldn't have. Yep. You've been waiting, huh? Tight patience. Yeah, it's too late. The drop window, I can finally say that I own you for the rest of the year. All right. So we'll start easy. And that's just with the definition of what an acid and a base is. Scientists can't really figure out, so there's actually 3 different definitions of an acid and a base, which is just kind of ridiculous, but whatever. Here you go. The first one is Arrhenius. The Arrhenius definition of an acid is the one that you're used to. It's a substance that when dissolved in water increases the concentration of hydrogen ions. Hydrogen ions is just H+. So like when we put an acid like HCl into a thing of water, that acid dissociates into H+ and Cl-. All right, so the H+ has gone up, the concentration of it. So that would be defined as an acid. Pretty much everything we've used as an acid all year long started with an H, and when it broke apart, it increased H+. All right, a base, all right, substances that when dissolved in water increase the concentration of hydroxide ions. And so we're kind of used to that as well. If I put NaOH in here, it dissociates into Na+ and OH-. So the concentration of OH- has gone up. All right. Now, this entire chapter and the one after it has a lot to do with being in water. So when we talk about water, we need to think about the actual chemistry going on inside the water itself. And that is this reversible reaction of hydronium and hydroxide forming water. Okay, it's a super easy equation. It's just the association of these 2 ions to form water, or the dissociation of water to form these 2 ions. Yeah, go ahead. For video purposes, Isaac just said, is it constantly dissociating? And yes, it is, but it's not acidic or basic, because every time one of these falls apart, both of these are formed. So your H+ in pure water will always equal the concentration of OH-. This is just tripping out. So if they equal each other, then it's still neutral. And it'd be meaningless, and it is meaningless. In just pure water, we don't have an imbalance in H+ or H-, so the pH just stays 7 or it stays neutral. All right, but then we come along and we add an acid or a base, and then things go haywire. Because if I add that hydrochloric acid, that makes the H+ now go up. If this goes up, this will actually go down due to the Chatelier's principle. And now we have a lot of H+ and a little OH-, and we would define this substance as an acid when H+ is in higher concentration than OH-. Okay, vice versa, if I back all that out And now I add a base. So the hydroxide goes up. That makes more water form, which means the H plus goes down. Now I have a large concentration of OH minus and a small concentration of H plus, and we would say this solution would be basic. Okay, so it's all happening in water. Just naturally, water itself, it does ionize. It's called the self-ionization, and not a lot, but it does. But if they're equal, it's neutral. All right. Now, here is a second definition of an acid, and none of them are that hard, but it's called the Bronsted-Lowry definition. And it says that an acid is a proton donor. Say that louder. Not all of them do. Whenever you say all in chemistry, I get nervous, but pretty much, yes, that works. Okay, now, our acid, still a proton is labeled as an H plus. So we're still looking at something like HCl. Same thing, the H breaks off, it's an ion, which is the proton. So an acid donates one, a base can accept one. Okay, so your OH minus, it's hanging out looking for something positive to hang out with. It can find an H plus, and they kind of neutralize, and now you have H2O or HOH. Okay, so it's not much different than you're used to with the Bronsted-Lowry. It's just a different way of looking at it. The acid will always give away its proton. The base will always take it. All right. Next. Well, here we go, I guess. So a Bronsted-Lowry acid must have a removable or acidic proton. Okay, there's got to be an H hanging out there that can be taken away. Now, not everything with an H is it removable. So like HCl is great, but like CH4, none of those H's are removable. Okay, this does not dissociate when placed in solution. This is methane gas. Okay, so this would not be an acid even though it has an H. The acids pretty much have the H at the front, and they will dissolve when placed in water. Or dissociate is the better term. Okay, a Bronsted-Lowry base doesn't have to have OH. That's the main difference now. It just must have a pair of non-bonding electrons. Okay? And that's why ammonia can be an actual base, even though it doesn't have OH in it. It can act like a base because it had this pair of electrons here that was not bonded to anything. Those electrons put a negative charge on this side of this molecule, and if a proton comes along that's a positive, it's missing both of its electrons, it'll be attracted to that spot and it will stay there. And so our NH3 accepted a proton to become NH4. Okay with that? Is that all right? Okay. Now, sometimes you can have something that will donate or accept. And if you have something like that, it's amphiprotic. And that's a word you should know. Amphiprotic. It means it can donate an H or it can give an H. Some examples are hydrogen carbonate, hydrogen sulfate, and water. Oops, I don't want to do that. I wanted to undo. Does that make it too confusing? All right, so I'll just redraw it, but I'll talk it through as I do it. HSO4 minus came from H2SO4, losing one of its hydrogen ions to become HSO4 minus. All right, and then it could lose a second one to become SO4 minus 2. This is a minus right here. You okay with that? So you'll notice this middle step, it could gain that H and go that way, or it could have given that H off and gone that way. So it can act, if it goes this direction, it would act as a base. If it goes this direction, it would act as an acid. Because here it would be accepting a proton, and here it would be donating a proton. So amphiprotic, it can move the proton either direction. Okay, water can do the same thing. So here's water. Actually, I'm going to write it as HOH. Okay, HOH can be written as H3O plus. If it accepts an H, we call it H3O plus or hydronium. Or it could donate an H. This should be an arrow. And it can become OH minus. Okay? If it gave off an H to become water, HOH. If it gives off, it becomes OH minus. It can go either direction. So water is amphiprotic. All right. The next two slides are pretty important. So if you don't get them, ask me a question. So it says, what happens when an acid dissolves in water? So we kind of already described this, but water acts as a Bronsted-Lowry base and abstracts a proton from the acid. All right? Abstracts means it like removes it and then it will stick to it. So the water takes the H and sticks to it to become H3O plus. That leaves chlorine all by itself. Okay? As a result, the conjugate base of the acid and a hydronium ion are formed. Now, just for a minute, we need some vocab here. A hydronium ion is defined as two things that are actually the same thing, even though they won't look like it. Hydronium is H3O plus. Hydronium is often also referred to as H plus. Now, they don't look the same, but really they are, because H3O plus is really just a water molecule that had another H plus stuck with it. Okay? And you've probably noticed chemistry teachers are lazy, so we don't always just write this H3O plus when we can just say, hey, we know we have H plus in water now. Okay? But for this slide, you need to know hydronium is H3O plus. We okay with that? Okay. Going this direction, the acid donated, whoops, that's the R, a proton. Here, water was my base and accepted a proton. We okay with that? Now, going up though, and I'm going to write it under here. You okay with that? if we go back up in this direction, Cl minus accepts a proton. And H3O plus donates a proton. Okay, they're just opposites. Okay, so now we're going to introduce two vocab words. Chlorine is what we call the conjugate base. And H3O plus will now act as the conjugate acid. So what these things are, so the conjugate base is the thing that will accept a proton in the reverse reaction. It acts like a base. The conjugate acid is the thing that will donate a proton in the reverse reaction. Now, if you'll look, let's see if it'll let me change here. Let's go to whatever, orange. So here we go. The conjugate base is always the anion of the acid. I'll say that again. The conjugate base is always the anion of the acid. Are we okay with that? The conjugate base is always the anion of the acid. And then the conjugate acid always comes from what the base became. And that one's not as easy to remember, but if you can remember one, you'll be fine with the other one. The conjugate acid comes from what the base became. Okay, now the next slide is another example. So conjugate acids and bases, they come from the Latin word conjugare, I don't know, meaning to join together. Reactions between acids and bases always yield their conjugate base and acids. All right, so here's my acid. The anion is the last part, right? So over here, my conjugate base is the anion of my original acid. And then my base becomes H3O, and that would be my conjugate acid. So the reason this is important is because you have to be able to identify in a reaction all four parts. The acid, the base, the conjugate base, and the conjugate acid. Okay, I think the next slide is like 10 examples. Do you need more time on this slide? Following reactions, draw an arrow that represents the proton transfer between reactants. Then identify the acid and conjugate base and the base and conjugate acid below each other. All right. So what we're going to do is we're going to take this and tie it to that, and this and tie it to that. Now we're not doing oxidation and reduction, so don't stress about that. That's just showing you your differences. But this thing here, this is your acid. Now, it looks different than any acid you've ever seen before because the H is actually on the end. All right. This is ugly. This is really just acetic acid, which we have written as HC2H3O2. These are the same thing. This is the structural formula. This is its chemical formula. All right. This thing, if you'll notice, is the anion of my acid, which means it's really my what? Conjugate base. You okay with that? All right. Now, that must mean H3O is my conjugate acid. And that must mean water is my base. Will you That's a trick question. Most of the time, absolutely. Okay, give these a shot. All right, here. This one's typically easy because HCl is just always an acid. This is its anion, so that's the conjugate base, correct? All right, and then the conjugate acid has to be on the same side as the conjugate base, so that must be there, and that must be, this is your base. Fair enough? All right. Now, NH3, when it goes from here to there, what is it doing with an H? Is it donating or accepting? It's accepting, so that means NH3 is the what? Base. No, don't get mad that the base was written before the acid. There's no rule. All right? So the base, all right, it's tied then to the thing that will donate the H the other way, so that's your conjugate acid, which means this has got to be your conjugate base, and then that leaves you with your acid here. Okay? Typically, I would have found the acid first and gone from there, but it doesn't really matter. Okay, now, you'll notice NH4 is on the left here, but that's fine. We can live. NH4 goes from NH4 to NH3. So if it gave away an H, what do we call it? An acid, which means this must be the conjugate base. And it doesn't look like the anion, because it's not technically even an ion, but it is the anion of that thing. It just happened to be that that was a cation. And that was one of the weirdest sentences maybe I've ever said out loud. But it's true. Okay? If this is your conjugate base, then this must be your conjugate acid, and this must be your base. All right? And we can prove it. The base accepted an H to move from here to there. So it did act basic, or going from here to there, the conjugate acid gave away the H. Okay? Oh, there was more, but we'll just call it good here. All right? HClO goes to ClO minus. So there's your acid. There's your conjugate base. That means this is your conjugate acid, and there's your base. Are we okay with that? All right? It's like if I just asked you without this, it's hard, but once we go over it, they're really not that bad, hopefully. Okay. Acid and base strength. All right. Strong acids. I think we've talked about electrolytes and defined them. Strong doesn't mean they're super reactive. Like they can be, but that's not its definition. Strong means it dissociates completely when placed into water. Yeah. What's that? Weaker bonded together, yeah. Which is kind of weird. And yeah, Reyes said, is that when you did the light bulb thing? Yes, that's what when we did this. Okay? And it actually does make sense why we would call it a strong acid if it dissociates a lot. Because if we put HCl in water and all of it breaks apart, then we get a really high concentration of H+. Or we get what we call a strong acid. But if I put in a weak one, like acetic acid, I put it in, it's really weak, which means we just barely mess up the H+ concentration. So there's not a lot of H+, so we'd say it's a weak acid. Okay? It does make sense why it's defined the way it is. It just isn't what we're used to. All right. Now, here's another way to look at them, and this is important for chapter 17, like super important. The strong acid also is defined that their conjugate bases have negligible basicity, meaning they resist protonation. And I'll tell you what that means. I see some people writing, so I'll tell you what that means in a second. Is if I add HCl to the solution, it will make H plus, and there'll be some Cl minus, right? Okay? If I add just straight H plus, I'll mess with the pH. But if I pour in table salt, nothing will happen to the pH. Because the Cl has no ability to grab an H to form HCl. Because the Ka, which we're going to learn about, favors the ions or the products way more than the reactants. Okay, but this is weird. I can have water and I can add sodium acetate and it will mess with the pH. Because what I'm going to do, I'm going to get some Na plus, and then my acetate ion, it's the conjugate base of a weak acid, so it's going to go find the H plus that was in here because water breaks apart to H plus OH minus. This will find that H plus and cause its concentration now to go down because it will now be tied to an H. To an acetate. And if H plus goes down by Le Chatelier's principle, what happens to OH minus? It goes up. So this is unique. I have added the conjugate base of a weak acid and turned the neutral solution basic. Because the concentration of OH is now larger than the concentration of H plus. Now, that only applies to weak things because strong things stay dissociated. All right. You can define it that way, which is weird, but absolutely. Okay. Now, when we say this chapter is a 10 eventually, it's because we got to do the math of all this stuff. It's not awful. Whatever. It's doable. All right. So weak acids only dissociate partially in water. Their conjugate bases are weak bases, which means they will grab the H plus from the solution. All right. Hey, we're about out of time. There you go. I like that. Okay, this is just last year's explanation of the same thing, so we'll call it good. We got a minute and a half. So I would read the first couple sections of chapter 16 over the weekend. Brindley, it's an assignment for you, though, because you have to have motivation, I've been told.